Okay, we're going to talk about what a cylindrical shape will do to light rays, how it bends them, where it directs them. And let's start out with this surface right here because it's the easiest one. It's going to be perfectly flat and smooth. Does a flat surface refract light? Well, sure it does. As long as the light is coming from a substance, a medium of one density into a substance of a different density, and the light is not going in perpendicular to that flat surface. Because if it's perpendicular to the flat surface, it's not going to bend. It's just going to slow down, but it's going to keep going straight through. If the light's coming in at an angle, and if the two densities are different, sure, that's Snell's law. It will refract the light. What it won't do is converge the light or diverge the light. In other words, light rays that come into the surface at an angle and the light rays that come in are parallel to one another, they will all be refracted, but they will also leave parallel to one another. Now for the vertical surface on the remaining side of the cylinder, if I were to hold a pencil up against it, anywhere along it, you would see that that pencil lies flat against it. That's a flat surface. Horizontally, it's curved, but vertically, all the way around, that pencil lies flat. So when light rays pass through here, the vertical surface there is not going to converge or diverge the light rays. The light rays will maybe refract, but they'll come out parallel if they went in parallel. Now the horizontal surface is going to converge those parallel light rays towards the center. It's going to converge them. And if you look from the top of the cylinder down, you can kind of see the path, the direction. And you really need to use your imagination here to imagine that those orange lines are no longer individual lines, but just one flat sheet, one plane of light. And then imagine the yellow ones coming from the other side are one plane of light, like a piece of paper, orange piece of paper and a yellow piece of paper. And they would eventually meet, and then if one could go through the other, and then cross. Okay, and then imagine everything in between filled in solid with light. So what you actually end up with, because I know it's hard to imagine, is a vertical line focus. I wanted to explain what the light does when it goes through a cylindrical shape, but the shape of an astigmatic cornea is not cylindrical, is it? It's spherocylindrical, which means that it doesn't have that flat side that we held the pencil up to. It does have that very curved side like a cylinder, but the flat side of a cylinder in a spherocylindrical surface is also curved. It's just not curved quite as much. Now we have a horizontal curve, which is a tighter, steeper curve, and we have a vertical curve, which is a flatter curve. And remember what happens, what the difference is between the flatter curve and the steeper curve. One's going to have a shorter focal length, and so we're going to have two focal lines. We're going to have a shorter one caused by the horizontal curve, and that's interestingly enough going to make a vertical focal line. And then we're going to have a longer focal line farther away from it, that's going to be caused by the horizontal aspect of our lens, our cornea in this case. And that's, interestingly enough, going to be a horizontal line. And that's just because of the orientation we have. We're doing an against the rule here. If we were doing a with the rule, we would flip that. And sorry for this picture, but it is really hard to draw this. What happens with a sphere cylindrical shape is it creates two focal lines. In this case, because of our orientation of the cylinder part, in other words, it was like a cylinder, like a can of pop sitting on a counter, rather than lying on its side. We have it the long end vertical. Because of that, what it creates is a vertical focal line anteriorly and a horizontal focal line posteriorly. So in the picture, in other words, the vertical focal line is the red line, and the horizontal focal line is the purple line. And the area that we're concerned with here right now is the area in between these two focal lines. That area is called the Interval of Sturm. And because it's so hard for me to represent that area in a picture, you can actually get an idea of what this is going to look like if you take a piece of paper and roll it up and then pinch one end with your left hand, pinch the end, left end vertically, and then with your right hand, pinch the right end horizontally. And that's kind of the shape that is created by this. I mean, it has a little, it doesn't quite go straight across. It has a little dip in the center, kind of a little narrower in the center, but it's close enough that you can understand what I'm talking about when I say Conoid of Sturm, because this shape is similar to a conoidal shape, or a conoid. Okay, so the Conoid of Sturm is the area in between the two focal lines that are created by light passing through a spherocylindrical surface, the cornea or an eyeglass lens. Okay, so here we have the vertical one represented with the red line and the horizontal focal line represented with the purple dash line. But where does this fall, this conoid, in relation to the retina of the eye? Okay, because let's say our spherocylindrical, well, we are saying our spherocylindrical surface is the cornea of the eye. So it creates this somewhere. Where? Okay, here I have the conoid represented in a slightly different way, but you can see it's that area in between the two focal lines, the red and purple dash line. And in this case, both of them are in front of the retina. And we already know that that means that this patient has compound myopic astigmatism. And this patient has compound hyperopic astigmatism. Simple hyperopic astigmatism, simple myopic astigmatism, and mixed astigmatism. Okay, now we're going to take our patient with mixed astigmatism again. And we're going to move this conoid of Sturm around and try to imagine what the patient might be seeing, because it's going to vary depending on where on the retina it lies, which part of it lies on the retina. In other words, let's put it that way, which part of it lies on the retina. So let's go back to our rolled up piece of paper that we were using to represent this conoid of Sturm and dissect it, okay? We're going to take little slices out of it and imagine that that was the slice that fell on the retina. What shape would be on the retina? Okay, so we can see when we do this cross section, see what this light looks like, that if this conoidal shape fell on the retina closer to our vertical focal line, actually the closer it was to the vertical focal line, the more distorted the image would be oblong, like vertically distorted. And the closer that we got to the horizontal focal line, the more distortion would be horizontal of the image. Somewhere in the middle there, though, actually exactly in the middle, it would be no distortion. It would be round. That's a blur circle. It's not a fine point. It's a circle, a blurry, but it wouldn't have the distortion of being drawn out vertically or drawn out horizontally. And that is called the circle of least confusion. Confusion referring to distortion, like a confused image. The image is least confused right there. You could say circle of least distortion, but back in the 1800s or whenever this term was coined, it makes more sense to say circle of least confusion, meaning the image is least confused right there. And when we take a spherical equivalent, what we're trying to do is put that circle of least confusion right on the retina, because it's still a blur circle, but sometimes depending on the distance between the two focal lines, the smaller the distance between those two focal lines, the smaller that circle's going to be. And I think we said in the first video that the larger the blur circle, of course, the blurrier it is. The closer you get to a small point, the finer the visual acuity will be. Okay, now collapsing the conoid of Sturm is our goal when we're refracting a patient, when we're trying to find the eyeglass lenses or contact lenses that is going to get rid of this two focal lines and turn it into one focal point right on the retina. Collapsing the conoid of Sturm. Okay, so here's the uncorrected eye. And up in the corner there is the eyeglass prescription of the lens that will correct this astigmatism. Okay? So first of all, the -3 does this. Then the +2 does this. Well, actually, it doesn't. It collapses everything into a focal point on the retina now. I just wanted you to see by using the lines what I was doing. Now, the first question is probably, how come the -3 moved everything back and the +2 didn't move everything forward? It just moved the purple line, the posterior line, forward. Well, it's a really easy answer. I started out at the beginning of the first video talking about how spheres focus light all the way around. They focus it equally all the way around. And -3 is a sphere power, so -3 affected both of those focal lines. Then I talked about how cylinders focus light. Not cylinders, cylinders. Remember, I specifically wanted to talk about cylinders because one side is straight, one side is not converged or diverged. It's only the other side that is. One axis is, one axis isn't. +2 is a cylinder. And it's very important that we get that cylinder in the proper axis so that we can collapse in this case, it was the horizontal line that we needed to collapse, that purple dashed line that we needed to collapse with the cylinder power. And the truth is, by now you should be able to do these power crosses in your head. They're so simple. You should be able to just look at this prescription and know. And why do I say that? Well, remember the quick way to do a power cross? I'm given this prescription and plus cylinder, and I transpose it into minus cylinder. And then the -3 goes at the 180 degree axis, and the -1 goes at the 90 degree axis. Or if you want to do it in your head, do it a little bit quicker. You know that this goes here, and then your next number is going to be combining these two, and that's going to go 90 degrees away. Okay, now we have our power cross. And we know that the power cross represents the prescription that's actually on the correcting lens. Okay, so this is the actual power that's on the lens that we will correct this astigmatism. And remember what the astigmatism looked like. Okay, both of those lines were in front of the retina, compound myopic astigmatism. And for clarity, I'm not going to show the eyeball and I'm not going to show the cross section. I'm just going to show my red vertical line and my purple horizontal line. And you just have to remember that the red is in front and the purple is behind it. Okay, now this is the part you're going to have to really pay attention to, because if you don't, it'll be a little too tricky. Look at the orientation of this cylinder and the power that's on the lens. Okay, and remember that with a cylinder, that flat side, that in this case on that cylinder is horizontal. Remember, you could put a pencil up against it. It's flat. That's the side with no power. All of the power in this cylinder that's drawn here, all of the power is at the 90 degrees because that's where you have that steep curve. One side is flat, no converging or diverging power. The other side is curved and it has all the power, in this case -3 of power. And that -3 of power at the 90 degrees is acting upon the red line that's anterior on the eye. It's giving it a -3, which, if you think about it, it was about 3 diopters in front of the retina. So a -3 will push it back right onto the retina. And then our +1 acts upon the purple line, which was about 1 diopter in front of the retina. And it gives it a -1 and pushes it back onto the retina. So that's how this type of a lens will correct the compound myopic astigmatism. And that's the end of this video. I'll pick up right where we left off in the next one. Thanks for watching.